In this module, we are going to talk about embedded control with NI myRIO, and specifically what we are going to do is to develop a state machine using NI LabVIEW and embed the state machine as a real-time application on the NI myRIO. So we will explore how we can communicate between a PC and the myRIO and vice versa, how we can send data from the myRIO to a PC. So let's go first of all to the problem statement to go over what we need to build in terms of our state machine. So, in this model, we need to develop a fully embedded application on myRIO to simulate the control of a skid steering robot. The robot has two independent wheels that can be controlled independently. Each wheel will be represented by two of the LEDs on the myRIO according to the following. The left motor will be controlled by LED 0 and it simulates the motor going forward. And LED 1, it simulates this motor or the left motor going backward. The right motor will be controlled by LED 2 and this simulates this motor going forward, and LED 3, it simulates the motor going backward. If both LEDs are off, then the motor is off. If both LEDs are on, then the motor is in a brake state. In other words, we can brake both motors. If the four LEDs are on, it means the two motors are in the brake state simultaneously. Now, for the requirements of our state machine, let's go over them in order to understand how we should draw or develop our state machine diagram and then how to code it in LabVIEW. First, when the user presses no key on the keyboard, on the physical keyboard of the PC, both motors should be off, which means there is no input from the user. Second, when the user presses the forward arrow or on the keyboard or the W key, both motors will turn forward. In other words, here LED 0 and LED 2 must be turned on in order to simulate the motor moving forward. Third, when the user presses the backward arrow on the keyboard or S, both motors will turn backward. Fourth, when the user presses the left arrow on the keyboard or A, the left motor will turn backward and the right motor will turn forward. In this case, we are creating a torque in order to steer the motor to the left. Fifth, when the user presses the right arrow on the keyboard or D, the left motor will turn forward and the right motor will turn backward. 6, when the user presses the spacebar, both motors should brake. In other words, all the four LEDs must turn on. 7, the myRIO should run independently from LabVIEW. In other words, we need to create a real-time application and embed it on the NI myRIO. 8, you should have an application on the PC that runs independently from LabVIEW. So we need to create a PC application, a LabVIEW PC application. 9, when the user presses the button on the myRIO, the motor should brake and override any command coming from the computer application. So in this point here, this is where we need to communicate or send data from the myRIO back to the PC in order to override whatever commands we have coming from the PC. Since we need to indicate this state that the push button is pressed physically on the myRIO on our PC application. That's why we need the communication from the myRIO or to send data from the myRIO to the PC. 10, you should have indicators on the front panel of your computer application to show the status of each LED. 11, you should have an indicator on the front panel of your computer application to show the status of the myRIO button. Now for the bonus here, we are going to deal with the second point. When the myRIO starts, blink all LEDs for 5 seconds before the user can do anything. So this will simulate the initialization state in our state machine. So that's it for the given. Now, since we have a complete understanding of the given, the next step is to build our block diagram before we start coding in LabVIEW. So what we have here is our block diagram or our state machine in the form of blocks. So the first thing that we need to do is we need to have an initialization state where we need to initialize our controllers, indicators, everything. So this step is, or this state is an essential state in every state machine that you build. Now we have the other states. We have the move forward state, we have the move backward state, we have the move left state, move right, brake, motors off, and finally we need an essential state, which is the exit or shutdown state. In other words, whenever we dealt with our robot, what do we need to do when we're done working or dealing with it? We need to, of course, shut down everything. So we always need an exit state in our state machine. Now, whenever the initialization state finishes, what we need to wait for as users, or what the code or our LabVIEW code should wait for, is an input from the user in order to go to a certain state, one of the 1, 2, 3, 4, 5, 6, and 7 states. Now, for that, we need an idle state. And in this idle state, what we will have in the code is just an event structure, as we will see later on, that it will wait for an input from the user through the keyboard in order to get us to one of these states. For example, once the initialization state is done, our state machine will go directly into the idle state. Now, what will happen is, as soon as we press the W command, and here we have lowercase w and uppercase W, which means our key should be case insensitive, we go to the forward state. If S is pressed, we'll go to the backward state. If A is pressed, we'll go to the move left state. If D is pressed, we'll go to the move right state. If the space bar is pressed, we'll go to the brake state. If no key is pressed, we'll go to the motors off state. And if the stop button is pressed, we'll simply exit and shut down our robot. Now, there's something here that is really important. Whenever we press the W key on the keyboard, we'll move to the, or our state machine will go directly to the move forward state. Our robot will start to move forward. And while it's moving forward, we will go back to the idle state. In other words, we will see later on that our event structure will take the last value, which is the move forward, and the last value will be the value that is taken by our robot. So this is why whenever we go to the move state, we need to go back directly to the idle state. Now, when we go back to the idle state, as soon as, or as while the W key is still pressed, the robot will keep moving forward, although we are in the idle state, but it will wait for another input. As soon as another input is pressed, for example, S, the robot will go to the move backward state, for example. And this is something super important. So we need to always go back to the idle to wait for another input, although another state is running. And we know that the other state will be running due to the event structure in LabVIEW, as we will see in a bit. So that's it for our state machine. And this is why you see here the arrow is going forward and backward as well. Now, what we need to do is to go to LabVIEW and create a myRIO project. Now, for our myRIO project, let's call it right there, our skid robot. And for saving it, we can save it in our embedded control with NI, choose current folder, and then create our project or myRIO project. Now, as you can see here, in my project tree, we have two targets. We have our PC and we have the NI myRIO target. So remember that we can run a LabVIEW code on the PC because the PC is a target by itself, and we can run a LabVIEW code on the NI myRIO. Now, obviously, in this example or for this state machine, we need to build it underneath the my computer, or under our target is, or it will run on the main PC, and then we need to communicate whatever state we have back to the myRIO in order to turn on and off the LEDs of the myRIO. So what we are going to do, we are going to right click on my computer, go to new, and then VI. And here, what we want to do is we want to start building our state machine. So the first thing we are going to do is to create an enum. And for that, we will call it states. And for our enum, we need to add the different states that we have. So the first one will be the initialization state. The second one, our second state will be the idle state. Third, move forward. Fourth, move backward. We'll have turn left. We'll have turn right. We'll have the brake state, and we'll have the motors off state, no key is pressed, and finally the exit state. Now remember here, we have 9 states in total. So the index of the first state is 0, the index of the last state is 8. So we have 9 in total. So we need to delete this one since we don't have a ninth state. And this is super important. Otherwise, you will have an empty case in your enum. Now we are going to press OK. And if I click here on my enum, I can see my different states right there. Now we want to start building our state machine. So let's go ahead and build it. So the first thing we are going to do is to create a while loop, drag it all over our code, and then we're going to create a case structure. Now for the case structure, what we are going to do is wire all these cases in our states variable or our enum, okay, that we name states, to our case structure to have the different states in our case structure. So for that, I'm going to right click on my states, create a constant, wire it to my while loop, and then feed whatever states I have to my case structure. Now, if I go to the cases right there, I can see I have only 2, but we need all the cases. So simply just right click on it and say make or add case for every value. And now I can see the different states right there. And this is super nice. Now we have all our states. All what we need to do is to start coding based on the given. Now, before we do that, or before we start with the initialization case, what we need to do is to always remember that we need to have a shift register in order to keep feeding our states to the current loop from the previous loop. Perfect. Now in the initialization state, remember that what's required is to flash the LEDs for 5 seconds, and after 5 seconds we need to exit and go directly to the idle state. All right, so for that, what we are going to do first, we are going to choose the elapsed time, and we're going to uncheck the automatically reset after time target because we need the time to run continuously. And then we will compare that time, the elapsed time, to a constant of 5 seconds. Now, if the time is larger than 5 seconds, we need to go to the idle state, or our state machine will hop to the idle state. If the time is less than 5 seconds, the state machine needs to stay in the initialization state. So for that, we can go to comparison and choose the select operator. Now, the select operator has 1 input or 3 inputs and 1 output. And the output will depend on the Boolean value right there. So if this Boolean value is true, I will get the upper value, which corresponds to the true. Now, if it's false, I will get the lower value, whatever is lower to the lower value, which corresponds to false. Now, for us, we need to feed the states. So what will happen is the following. If it's true, if it's greater than 5, we'll go to the idle. If it's less than 5, we're gonna stay in the initialization state. And for that, we are going to wire the output of our select operator to the shift register. And this is why we need a shift register. As long as the time is less than 5 seconds, the output here of our select operator will be the initialization state, and it will keep looping in the shift register until this condition is true, and then we'll go back to the idle state. Okay, so now we have it right there. Now we know what we want to do. Now what we want to do next is we want to flash the LEDs. So for that, I can also have an elapsed time structure right there. And for this elapsed time, I will automatically reset the time target after 1 second. Okay, so what we will do is we will turn on the LEDs for 0.5 seconds and then off for another 0.5 seconds. And this elapsed time will keep changing between 0 and 1. Whenever it reaches 1, it will automatically reset and go back to 0. Now, of course, we still don't have the LEDs here to do whatever we want to do. So let's go ahead to our front panel right there and create our LEDs. So we have LED 0, which will simulate the forward state. We have LED 1, which will simulate the backward state of our left motor. And we have LED 2, which will simulate the forward state of our right motor, and LED 3, which will simulate the backward state of our right motor. Now let's go ahead and align everything to have a neat front panel. And then what we can do is go to decorations right there, choose a flat box. You can choose whatever you like. You can change the style, the colors, you name it. Okay, so here we're gonna have one box for our left motor and another one for our right motor. And now what we are going to do is just right click or double click there and say left motor. And I'm gonna copy this one and say here we have right motor in order to be able to distinguish the LEDs. So this is for visual purposes. Perfect. So now we have our LEDs. Now, if we go back to our block diagram, we know that our LEDs will pop up right there. Then we can put them right there, align them, and then we can use them or create local variable for each in order to use it in our code, in order to change the state of each of the LEDs depending on the state that the robot is in. So for flashing the LED, we know that if the elapsed time is greater or less than, let's replace it, less than 0.5 seconds, that's what we need. If it's less than 0.5 seconds, what will happen is all the LEDs will be on, and if not, all our LEDs will be off. And that's super cool, as we will see once the LEDs, once we run and test our code. Okay, so this is it. We have the second one. You can align the wires so they look really nice. And that's it. That's pretty much it for the initialization state. So for our initialization state, now whenever the time is larger than 5 seconds, we're gonna go ahead to the idle state. Whenever the time is smaller than 5 seconds, we're gonna flash our LEDs to simulate an initialization state. Perfect. Now, one more thing we need to do, since here the hopping between the states happens automatically, we don't need our enum here for the states to be a controller. We need it to be an indicator. For that, I can just go ahead and say change to indicator. And simply what I like to do is to put it inside my loop in order to indicate the state or in which state am I. So, or my code is executing. So I can see it directly right there on the front panel. So this is it for the initialization state. Now we are going to go directly to the idle state. Now in the idle state, what we need to do is to wait for an input from the user in order to execute a certain state, whether going forward, backward, braking, etc. So for that, what we need is an event structure. And the event structure will allow us to take input from the keyboard and communicate this input to the myRIO later on. But most importantly, we will be able to go to a certain state depending on the input. For example, if you go back to our block diagram, If W is pressed, we need to move forward. If S is pressed, we need to move backward. And if any of the other keys is pressed, for each of the keys, we need to go to its corresponding state. Perfect. So this is what we are going to do. So the first state here, or the first event in our event structure, is the timeout case. And in this event or case, in the timeout, the code will execute whatever happens after we press any key or we release all the keys or whenever an event happens. So after any event happens, we will have a certain time before the event structure will go back to the timeout, and whatever is executed here, whatever is put here in the timeout structure will be executed. So usually this time can be around 20 seconds. We don't need more than that. It depends on your application. For our state machine here, 20 milliseconds is perfectly fine. Now, whenever we are in the timeout structure, where we need to go is to the idle state, which means we'll go back to the idle state in order to wait for a new input or to check what the user desires in terms of inputs. Perfect. Now, this is for our timeout. Now, next, what we need to do is we want to check whether a key is pressed. So for that, we can right click and say add event case. And for the event source, we can choose this VI since we want to check for this VI what's happening on the keyboard. And in terms of keys, we want to check first whether a key is down, whether the W, so let's go back quickly to our block diagram. For the state machine, if WSAD space, if one of these is pressed, we need to go to a certain state. So we need to keep checking whether one of these inputs is there using our event structure. So we'll choose key down, and as you can see now here, I have another or a new state, which is the key down. Now, for us to be able to know which key is pressed on the keyboard, because we need specific keys, we need to look up for the character in terms of the ASCII code for each of the keys. Now, here we are going to do it in a slightly nicer way. Instead of checking the ASCII code character, we are going to convert the character to a string, and then here the cases will be just directly strings instead of finding the ASCII codes for our characters. In other words, instead of going to the ASCII table, for example, for the space, it's 32. Instead of feeding directly the characters and putting there 32 for the character, we will just put the space, okay? So the space value there inside our case structure because we will convert it to a string. For uppercase A, for example, instead of typing in 65 and for lowercase a 97, we'll just type in uppercase a and lowercase a because we now convert these numbers to strings. And this can be done super easily in LabVIEW. So this is how we can do it easily. So what we are going to do is we are going first to convert our character using the conversion elements here to unsigned byte integer. So the first thing we're going to do is to convert it, and then we can go to numeric data manipulation, and I can use the typecast. So this will convert my character to the desired string. Now, all what I have to do is to have my default case in case nothing is pressed. Then I can add a case after, and I'm going to type in here lowercase w, uppercase W, enter. They will be entered automatically. Then add case after. We have lowercase s for moving backward, uppercase S. Add case after. We have lowercase a, uppercase A. Add case after. We have lowercase d for moving right, uppercase D. And add case after, we have the space, so we're just gonna type in here space, and that's it. Now we have our 4 cases. Now this true case, we don't need it. We can simply remove this case easily. Okay, so delete this case. And now we have the default case, moving forward, moving backward, moving left, moving right, and braking, or the break state. Now in each of these, we want to go to, in the default state, we want to just go to idle. In the forward state, we want to go to move forward, obviously. Now, whenever we type in on the keyboard S, we want to move backward. Whenever we type in A, we want to turn left. Whenever we type in D, we want to move right. And whenever we press the space button, we're gonna go to the break state. Perfect. So this is it for key down event. So whenever a key is pressed, now we are just taking whatever key is pressed right there, converting it to a string, getting it to our case structure, and accordingly going to the state that we desire. Now next, what about if no key is pressed? Let's go back quickly to our block diagram. If no key is pressed, right there, we need to turn our motors off. And for that, we need a new event. So I can right click right there, say new add event case, and I can click on new VI right there, key, and then key up. Now, whenever we have the key up, not key down. Whenever we press here on key up, it means that in this VI, whenever there are no keys pressed, this is what we need to do. This event will be executed, and wherever is put inside this event will be executed. For us, we need simply to go to motors off. Now we still need one event. What about if we press the stop button? Whenever we press the stop button, we need to exit. Obviously here we don't have a stop button. So what we are going to do is to create a stop button right there. And let's rename it stop, hide its label. And then what we are going to do is to have it right there for us. Again, I can align and distribute vertically nicely my variables. And now what I'm going to do is to add a case or an event case. And now I am going to choose the stop button. And whenever the value changes for this stop button, we need to stop the code. So if for the event source, we choose stop. For the event, we choose value change. Let's press OK. You can see here our third event is the stop with a value change. So whenever the value of the stop button changes, which means you press the stop button on your virtual front panel, you will execute wherever is in this event. So for that, we can right click and we know that we want to go to the exit state. And that's it. That's pretty much it. Now we have all our states. Now what we need to do is to decide what do we want to do in each of these states since we are done with the idle state. So in the forward state, what we want to do is turn the forward or LED on, which means LED 0, and LED 2 on as well. And for the backward ones, we need them to be off. This simulates our robot moving forward. So for that, I can simply copy my local variables here by selecting them and dragging. And for the move forward, what we are going to do, right click on all of them, create all constants. And for our move forward case, we need our forward LEDs to be on. So as you can see here, I have LED 0, 0, 0. You can just click on it super easily. 2 and 3 in order to have all our LEDs. So let's delete this one, copy these ones again. So we'll have LED 0 and LED 2 on. For our backward state, we are going to have our backward LEDs on. For our turn left state, for the turn left state, we need our right motor to move forward. So this is LED 2, and we need our left motor to move backward. Now for the right state, we need the opposite. For moving right, we need the left motor to move forward and the right motor to move backward. Now for the brake state, we need all our LEDs or all our motors to be off or on, in other words. It's the opposite because we're braking, and we said when the two of the LEDs are on for the same motor, it means the motor is braking. For motors off, all of them will be off, and for the exit state, all of them will be off as well. And that's pretty much it. Now we have everything that we need. But we still have one thing that is missing. When we move forward, these are the values that will be fed. Okay, so because we, in the idle state right there, whenever we type in, let's say, W, it means we're moving forward and we go to move forward. Perfect. Now, after 20 milliseconds, what will happen is that this event structure will go back to the timeout and back to idle. But this will not happen because when I press a key W, what will happen is our code will go to the move forward state, and now it will have whatever was last, whatever was pressed right there. So if I keep pressing W, I will keep moving forward. But even if if I keep moving forward, I want to go back directly to the idle state to wait for another input, even if I am moving forward. Perfect. So now we can move forward, move backward. We need, in the move backward, go to the idle state. In the turn left state, go again to the idle state. In the turn right state, go to the idle state. In the brake state, go to the idle state. And when the motors are off, again, back to the idle state. Now, whenever we are in the exit, we need to keep looping and stay in the exit state to wait for our code to stop. Now, one more thing. What we need to do whenever this stop button is triggered, what we need to do is, so let's go back to our idle state. So if the stop button is triggered, we'll go to the exit state. And in the exit state, we need to first make sure all our motors are off and that we stop our VI. For that, we can have a Boolean constant right there, a true constant, and we can wire this constant to our while loop condition, stop condition. Perfect. There you have it. Now I can still not run the code. Why? Because in all the other states, I need to wire a false constant for these. But the practical way of doing that is to just right click on the tunnel right there and choose use default if unwired. And by default, the value is false. And that's pretty much it. That's it for our state machine. Let's go ahead and test it to check if everything is running smoothly. So we can see that for the initialization, only one of the LEDs is turning on. Now if I press W, it moves forward, backward, left, right, and then braking. Now let's go ahead and see why. And it's pretty obvious. All of these are LEDs 0. So we can change them, run our VI again, and you can see now all of the 4 LEDs are flashing, which is great. Now we can go forward, backward, left, right, press the space bar. And that's it for our state machine. Perfect. Now we have our state machine, but now what we are going to do is to communicate these LEDs, the status of each of the LEDs to the myRIO. So what we have here is our NI myRIO in front of us, and it has the 4 LEDs, LED 0, LED 1, LED 2, and LED 3. And don't forget that we have the stop button right there. And we need, or the push button on the myRIO, and we need to use these in our state machine. So here's what we are going to do. So we are going to go back to our project tree, and underneath myRIO right now, we are going to create a new VI. We're going to go ahead and save this VI and call it myRIO controls or myRIO data. You can call it whatever you like. Now, for our VI here, what we are going to do is we are going to have our states. So the first thing we are going to do is to have a while loop and then wire its stop button whenever we want to stop it or whatever. So you'll see later on. Then we'll have our stop button on our front panel. What we want to do now, we want to capture the data from the PC application and send it through to the myRIO. How are we going to do that? Through what we call shared variables. So the first thing that we are going to do is to communicate our states, and then we need to communicate the status of each of the LEDs. For that, I can simply right-click right there on the initialization, or you can click right there, whatever you want, on the wire or on the initialization constant. And here I can create a shared variable or new shared variable. Now I have my variable right there. And this variable contains my states, which is great. This is what we need. Now we need two more variables. We need, or four more variables. We need one for each of our LEDs, and we need to communicate the data back to the NI myRIO. So for that, what we are going to do is the following. We are going to create four new local variables or shared variables. So new shared variable, right click create, shared variable, new shared variable, right click create, shared variable, new shared variable, right click create, shared variable, new shared variables. Now I have my four variables. Now in the PC application, I need to feed data to these variables. And in other words, I want to write to these. However, in the myRIO application, I need the opposite. I need to read data from these and communicate this data to my physical LEDs. Now, for every shared variable, I can right click on it and it has an access mode. I can either read or I can change its access mode to write. For us here, we need to read, and we need to read whatever is the current value that is stored depending on the state in our local variables. So for that, I can change these to change to read, change to read, change to read, and change to read. And that's the reason I am putting it outside the states, because whatever is the value, the current value inside of each of these states, depending on the state that the robot is in, this value will be communicated directly or it will be updated simultaneously to these outside of the state machine or decay structure. So this is why we place them outside. So let's just make sure they are nicely aligned. Okay, and now we have all the data that we need. Now, if I go back to the tree, I can see that all my shared variables are created underneath libraries. Usually, your shared variables will be stored underneath libraries. And what you need to do is to place them in a single library for this, at least for this state machine. So what I'm going to do, I'm going to select them and drop them right there. It seems that I copied this one. That's fine. This is LED2. Okay, I'm gonna put 2 here and 3 right there. Perfect. Now there you have it, LED 0, 1, 2. Now what I'm going to do, I'm going to remove the other library. So remove from project, okay, don't save all. I don't need them. And let's double check, we still have our variables right there. Perfect. So now, next what we are going to do is we are going to save in the same folder our variables, and I am going to name it my variables for the library skid robot. Perfect. Now, in order for my variables to work well, I need to place them underneath the myRIO target in order to have a successful communication. So I can simply drag and drop them. And as you can see here, I haven't saved the PCVI. And this is not a good practice. You should always save your work. So let's type in skid robot controls and call it PC, just to know that it's the PC application. Skid robot control. It seems that we have something here. Okay, perfect. Now it's working. So that's our skid robot control. It seems we have a problem with the shared variable. Let's see what it is. I can go ahead and right click it. Go ahead and reselect it. Go ahead right there and say LED2, go ahead right there and say LED3, and now it works fine. This is because I duplicated the LEDs by mistake there. Instead of dragging and dropping them underneath the libraries, I pressed the control button. So make sure you don't make this mistake. Now for this main VI, which comes by default, perhaps I don't need it, I can simply remove it. Now all what I'm going to do right here now, go to the VI underneath myRIO. So let's go ahead from there. So remember the myRIO data VI. And now I need to read data from these variables. So simply I can go to structures, choose a shared variable, and for this one I can select which variable. The first one is my states. Now I can duplicate these. So I will have 4 shared variables. And now I can select which one is for corresponds to which LED. So I have the 4 LEDs right there. So LED2 and finally LED3. So 4 LEDs in total, perfect. And now I can use whatever data is stored in there. Now let's look at something really nice. Now if I go ahead and create a case structure, what we want to do is to wire the states, and you will see 2 states only. Again, what we need to do is to right click and say add case for every value, and now I can see all my states right there. Now it's important to know that in this example, you don't need actually the states. I can just directly read the whatever is the Boolean values of the LEDs, and I can just have one single while loop with no case structure. So in other words, I don't need to read the states and then change the value of the LEDs in all of these states. But in some other applications where you have different actuators and sensors, you need to do that. For example, if each of the case corresponds to a different actuator rather than the left motor, right motor, etc., you need to do that. So for that reason, we are going to go ahead and uh, do it the way we will do it, just to have a general case. So in the initialization state, what we are going to have is, so first of all, let's change the access mode. Remember here we are feeding data. So access mode, right click, access mode, right click, access mode, right click, access mode, right. Now, by the way, to let you know, you can create a shared variable just from there. Okay, so from the tree directly, and you can, for the shared variable, it's network published, you can choose its name, and you can choose its data type, whether it's Boolean, double, integer, etc. So it's the same thing. So there are multiple ways of creating shared variables. Now the first thing we are going to do, actually the access mode here should be read, not write. Okay, is we are going to go to the myRIO library, go to LEDs. We want to turn on and off our 4 LEDs. And what we are going to do is to wire these inputs to our LED. And this is perfect. Okay. Since now we can, okay, now we can wire everything to our block. And this is in the idle state. We'll monitor what do we have there. We copy this one, we'll put it in the initialization state, then in the move backward, perfect, then move backward, the other one was move forward, turn left, turn right, brake, motors off, and finally the exit state. And that's pretty much it. Now we have everything we need. Now there's one more thing. In order to ensure a smooth communication between the PC application right there and our myRIO application, we need to have a slight time delay between the two. Otherwise, the stream of data from the PC will really overwhelm the myRIO. So for that, I can just have a nice multi-timer here. or nice wait. I can choose, for example, 10, 20 milliseconds, depending on the speed that you want. And on the NI myRIO, this one will be slightly smaller in order for it to be able to read a little bit faster. So I can have a constant here and I can choose 5 milliseconds. And now all what we need to do, so we'll have our myRIO right there. So the first thing we are going to do is to run our LabVIEW code that is on the myRIO target. So we'll wait for it to upload and deploy everything. I'm gonna save everything. So now it's running really smoothly, as you can see. And then we are going to wire or run our VI, which is right there. And now, in order for us to be able to see our camera at the same time, what we are going to do is to run it. So let's run it and let's see what will happen on the myRIO. So you can see now the LEDs on the myRIO right there are flashing. If I move forward, I'm turning LED 0 and 2 off, backward LED 1 and 3, left LED 1 and 2, turning right, and braking. And if I stop, the communication will be directly stopped. So this is pretty much it for the communication between the Arduino and the myRIO. Now we still need to do one more thing. If we go back to the given, they told us here that you should have an indicator on the front panel of your computer application to show the status of each LED. 11, you should have an indicator on the front panel of your computer application to show the status of the myRIO button. In other words, we need to have an indicator to check whether our myRIO button is stopped or not. And when the user presses this myRIO button, the motor should brake and override any command coming from the computer application. So here's what we are going to do. So first of all, we'll create an LED right there. And for this LED, we're going to type in here myRIO button. And for this myRIO button, okay, to check whether it's pressed yes or not, we're going to have obviously a shared variable for it. So this is our myRIO button, and we're going to check whether this button is pressed or not. Now we can check that, of course, we can get the data from the VI that corresponds to, or that is underneath the myRIO target. So for that here, I can just select the myRIO, go to the push button right there, and we know that what we want to do is, whenever this push button is pressed, we want to override any command from the PC. So here's what we're going to do. It's a very simple thing. So we're going to have another case structure right there. And for this case structure, we're gonna go and wire it to our input. Now, if this button is pressed, if it's true, I need to override and brake my motors. If it's false, I need to operate normally. So for us, this true case should be the false case. So we can right click and say, make this case false. And for the true case, we simply want to turn on or brake our motors. So turn the 4 LEDs off. So for that, we can just have our true case right there and simply right click on it and say create all constants. And now we have all the constants. Obviously, I don't need this one, and they will be all true since we need to break everything. Now, what we need to do is, of course, you can communicate this data back to your myRIO, to the PC application. In other words, these true values, you can communicate them back to turn on the 4 LEDs on the PC. I am going to leave this one as an exercise for you. But what we want to do here, we want to communicate back this Boolean value right there for our push button, whether it's true or not. So for that, I can just right click there, say create shared variable, new shared variable. And for it, it's called value. Now, perhaps you don't want to call it value. You want to call it something else. You name it. So what you want to do is go to the tree right there. And you can see you have your variable right there. So I'm going to first, okay, drag it and drop it right there. And I'm going to rename it. I'm going to say myRIO button. This is what I want to name it. I want to remove this library because I don't want this library. Save, and I'm gonna, don't save actually. And now I have this shared variable. Now what I'm going to do is I'm going to go to my PI right there, PC application, click on my select variable, say that I want the myRIO button, change the access mode to read because now I want to read from it. And then what I want to do is feed it to the myRIO virtual LED. Now let's run it side by side and see what will happen. So here's my myRIO application. Let's run it and save all. All right. And then next what we are going to do is go to our PC application. Okay. Let's show the myRIO before we run it. Okay. And let's run it right there. As you can see now, everything is operating smoothly, nicely. All right. Left, right, backward, space. Now, whenever I press the push button on my myRIO, let's do that. I'm going to press it. You can see the myRIO is turning, or the LED on my front panel on my PC application is turning on, which means now I am communicating the data from the myRIO back to the PC. And now we have two-way communication, and this is super cool. And whenever I press it, you can see the four LEDs turn on. And if I press it and try to do anything else, nothing will happen because you've overridden them. Now you have noticed here that even if I press the push button right there and I press W, something is coming right there. I'm seeing two of these are turning on. Why is that? Because as I told you, I will leave this one as an exercise from you. You need to communicate the values right there in the true back to your PC application. And that's pretty much it. Now, one more thing to note in this tutorial. How can we create, we said that we need a PC application that runs independently from LabVIEW, and we need a myRIO application, real-time application that is embedded on NI myRIO, which means that once you turn on your myRIO, the application will run automatically. So to do that, it's pretty simple. So for underneath the PC here, I can go to build specification, right click, and here say new application exe. Now for that, I can rename my application. I will save it right there in my PC, and I am gonna call this one, this application, PC or Skid Robot PC app. Perfect. Now for the source files, I want the skid robot control VI, and then I am going to build it. Now, if I go to this folder right there to the, I can see that I will have an application right there, which is called the skid motor application. So skid motor app, and this is your application. Now, if I open it, I have a standalone application right there that works by itself. So if I go to Windows, I can't see the block diagram because this is not a VI. This is a PC application, just like any normal app that you use. And you can see that the interface here, the color is a little bit different to indicate that this is an application. Now, also underneath the myRIO, I can create a new real-time application by going to build specifications again, new real-time application. And for that, I can also save it in the same folder and say here, skid robot myRIO real-time app. Now for the source files, you need two things. You need your VI, and for the inclusion, you need always to include your libraries. And then you're gonna click on build. Now what will happen is that you are building, or NI LabVIEW is building the real-time application. Now, once it's built, you will see the real-time application right there, and you can deploy it to your NI myRIO. You can set it as a startup, and you can run it as a startup. Why this is super important? If you can easily deploy it, and then you can say set a startup, and then I can say run as startup. And once you need to run it as a startup, the myRIO needs to reboot. Now, if I go back to the camera view here, this means that now whenever this application is deployed and ran as a startup, what will happen is that I no longer need this USB cable. I can just unplug this USB cable, and you can see rebooting here. And as soon as I power my myRIO, once the startup finishes, it will start automatically running the code that I have put on it. And that's super cool because you can have autonomous robots. Plus, later on, we will see that without the communication or without the USB cable, you can still communicate with the PC through Wi Fi as well. So you will have untethered robots in this case. So, this is pretty much it for this tutorial or this module. So this is it for state machines in LabVIEW. And this is it for how to communicate between a host PC and the myRIO and back from the myRIO to the host PC.